we move on to the diversification process. According to this figure, that is the last unit, we are going to perform this diversification on the fuzzy output. That means after we receive the input, and then after we performed the reasoning, and then right here we will obtain the aggregated membership function like this one. Yeah, for example, this one or this one, according to what kind of inferencing method we are going to use. Anyway, now what we are going to do is just to turn these aggregated membership function into the output, that is the value. So what kind of value int as the output y. Yeah, okay, now take a look at this one. So as I mentioned, that diversification, that is a process which is going to convert the fuzzy output into a numerical value so that this value can be used by the next stage. Yeah, so we are going to learn about all this method, that is the diversification method, and we have to make a decision which one we are going to use. Yeah, so that means different diversification method will give you different results. Some of them require more computations to compute the output. Yeah, okay, take a look at the first one. Now this is also called the height method. It is applied to a single peak output membership function. For example, the gray area. So it looks like this. We have a single pit. So what we are going to do is that we are going to identify the z value right here, the x-axis, that is the output label. So that means we are going to have a fuzzy inference system, and then the output, that is z. We have whatever number of input right here. So we would like to find out that when we have this membership function, the output membership function, and then what would be the value of z, that is the output. So what we are going to do is first identify the peak, that is the y axis, the y value, that is the largest, and then so now from this point, and then so we are going to locate the z value in the x-axis, and then so this will be the output right here. Yeah, so if we have this shape, and then the z star, that would be the output value. Yeah, okay. And the next method, we call this is the centroid method. This is the very general and commonly used method, or we refer to COA, the center of area, or the center of gravity. Yeah, we have two forms, continuous form and discrete form. Of course, right here we can have the discrete form as well, and I will show you that in the tutorial question. And now the continuous form, that is something like this. I'm going to explain that bit by bit. Z star, that is the z value in the x-axis, and then the same meaning, this value, that is the output of the fuzzy inference system. And now when we look at the denominator right here, so integration mu c and then z dz. So when we have a membership function, something like this, we call this envelope, that is mu c z. So when we are going to do mu c z dz, it means that we are finding the area under the curve. Yeah, so if we know the membership function, if we know the function of the envelope, yeah, so this is the area under the curve. Now, what about this one? Look at the numerator. So mu c, that is the envelope right here. So mu c times z, that is the z value in the x-axis. So what we are going to do, that is just to do the integration. This function times z dz, compute the value, divide by the area under the curve, and then so we will find out that, for example, it will give you this value. Yeah. Now the discrete form, that is the same meaning. Now assume that we have the membership function, we only have 3 values. I just call this is Z1, Z2, Z3. So Z1, Z2, Z3, they are labels. Yeah, so actually we have the numerical value. For example, this is 0.2, this is 0.5, this is 2, not in scale. Yeah, so this one may be 0.5, this one 0.7. What I mean 0.5, that is the value in the y-axis, and then this one may be 0.6, okay, in the y-axis. Now look at the denominator. The meaning of this denominator, that is summation of all these values, all these three values. So Z star, we will have 0.5 this value, and then plus 0.7 the next value in the y-axis, and then to 0.6, that is this one according to this label, that would be mu z z1. Yeah, so that is when z1, that is 0.2, we have 0.5 as the membership function. And now look at this one, we are going to do something very similar in the continuous form. Now the mu z, that is the membership grade right here, times the zi, so we will have 0.5, that is this mu z when z takes the value of zi, so times 0.2, so plus we still have z2, so 0.7, that is this value, okay, 0.7 times 0.5. Now move on to the next value, that is plus 0.6 times 2, okay, and then we can find the value of z. That is the way for us to find the centroid of the discrete form of the membership function, the output membership function. Now the next one, the weighted FH method. According to the name, that is we have to use the FH information. And now this one, the advantage, that is it is computationally efficient. You will just find out why it is computationally efficient, but we require that the output membership function to be symmetric. Now take a look at this example. That means, why do we have two trapezoids? It is mainly because we have two roots. Rule 1 and rule 2. So rule 1, which will give you the shape, that is, for example, this is the membership function 1, this is membership function 2, and then another one will give you membership function 2 right here, mf2, mf1. If you still cannot get why I have these two membership functions, just refer to this example. We have two roots right here. The first trapezoid, that is this gray area. The second trapezoid, that is this area. I'm not going to put them together, so that's why I have this membership function right here, and then I have this membership function right there. So two trapezoids. If we have more roots, and then so we will have more trapezoids as the output membership function. And now assume that we only have two membership function. This is the equation. This equation, that is now mu c, the summation of mu c times z bar. Z bar, that is the center. Yeah. So for example, mf1, a, that is the center of mf1 in the z-axis, in the x-axis, and then b, that is the center of the membership function 2 in the x-axis, the variable in the x-axis, that is z. So take a look at this example. Mu c for the membership function 1, that is 0.5. Mu c, again, this is the membership grade for membership function 1, times a, this a, that is the center right here, that is z bar. Okay, so this is z bar for membership function 1. Now plus, because we have the summation side right here, and then we move on to the next trapezoid, and then now mu c for this one, that is 0.9. So this is 0.9, and then times b. This is z bar for membership function 2. And then the sum of the membership grade, that is 0.9 plus 0.5. So we come up with something like that. And then once we know A and B, we can compute Z star, that is the diversified value of this output membership functions. Okay, now right here, we do not do rule aggregation. We just add on, we are going to use the information of each output membership function of each rule. Now, min max membership function, it is also known as middle of maxima. We require that the membership function, the output membership function, now we consider this is the aggregated one. So that means we come up with only one membership function, that is the aggregated one, that is this one. Yeah, so that is something like this. So now we require that the output membership function will have a plateau region. So right here, that is the flat region, and then we identify the A and B value, and then take the average, and that's it. Yeah, so that's why there's a comment right here. It is computational efficient. Yeah. The next one, center of sums. Center of sum, that is, we do not restrict to the symmetric membership function like what we have to do in this method. So it can be applied to any membership function. Now, again, now why we have two membership functions right here, or two shapes right here, because rule 1, this is from rule 1, this is from rule 2, the output membership function of rule 2. So we are going to consider that individually, and then so this is the continuous form. The idea that is very similar to the Centroid method. Now, but the difference is we are going to apply this equation to each output membership function separately. Yeah. Now take a look at this one. Mu ck, that is, because k equals from 1 to n, it means that this is the rule number. When k that is 1, we are talking about this membership function. When k that is 2, that is this membership function. That means we are going to compute this guy individually for each rule, and then put them together, sum them together. Now, mu ck, this is, for example, I call this is mu c1. This is the first membership function for rule 2. This is mu c2. So we have zk bar as well. Zk bar, that is the centroid. Yeah. So the centroid right here, that is, this is z bar 1. It means that it is for the first membership function, and then this one, that is set to the center of this membership function in the x-axis. So this is z2 bar, the subscript 2. It means that it is for the second rule. And now what we are going to do is just to apply this membership function like this. Mu c1 times z1 bar, that is 4. Yeah, so that is 4 right here, plus mu c2 times 8. Okay, so all of them, we are going to take the integration dz. Okay, we still have the lower bit right here. Yeah, and now when we do mu c1 dz, because this 4 is a constant, we can take it outside the integration. Yeah, so the same for 8. Mu c2 dz. Mu c1 dz, actually you are finding the area under the curve of the first trapezoid, and then this one, that is finding the area under the curve of this triangle. Yeah, so the lower part, that is the sum of the two areas of this triangle and trapezoid. Yeah, okay. This quick form, we are going to do a similar thing. Instead of using a continuous form, the trapezoid, it could be something like this. Yeah, so we have the nth root it looks like a trapezoid. So the meaning of this one, that is mu ck, yeah, because we still have the centroid right here. This is the set. So when we talk about the summation of all mu c, it means that we are going to sum up all these points. Yeah. So for example, this is 0.1, this is 0.2, this is 0.3, and so. Yeah. So that means we are going to sum up all these value, the y value, and then times the centroid right here. So I'm going to demonstrate this idea in the tutorial question. Now, that is when we look at this specific example, and so for continuous case, we have this value. So this 4, that is set k bar, that is set 1, that is this value as I mentioned. So 4 times this bit, that is the integration of mu c dz. This is a trapezoid, so we can just use this equation to find the area of the trapezoid. 4, that is the top, the length of the top, times plus 8, that is the bottom, the length of the base, times 0.5, that is this value, yeah, divided by 2, that is the area of this trapezoid. That means when you are given a trapezoid, the top is A, the base is B, and then the height, that is H. So that is A plus B times H divided by 2. That is the area. Move on to the next membership function, 8, that is the center right here. So this is Z bar. 4 times 1, it is mainly because the base right here, that is 4, times 1, it is because the height of this triangle, that is 1, divided by 2, this is the area of the triangle. Okay, and then the denominator, that is the sum of the area of the trapezoid, and then plus the sum plus the area of the triangle, and then we come up with 5.6. So this is the 5th method. Now, the center of largest area, the 6th method of doing the diversification, and so we have continuous form and discrete form as well. The continuous form, okay, so I'm going to talk about how do we do the diversification. That is when we are given a very complicated shape as the aggregated output membership function. What we are going to do is just try to separate this shape into subregion. Each subregion, that is a convex membership function. For example, when we chop this membership function right here, so we have 2 sub membership function. This membership function is convex, and then this membership function is convex. Okay, so now we are going to calculate the area. Yeah, calculate the area of these 2 sub-membership function. We just find out that this one which give you the largest area. So that's why we only apply this equation. This equation, that is the Centroid method. We only apply the above equation, the Centroid method, to this membership function, but not this one. Yeah. Okay. So this is the discrete form, because this equation, that is exactly the same as the Centroid method we talk about right here. So I'm not going to repeat it. Yeah, but we will see an example in the tutorial. Yeah, the 7th method, first or last of maxima. So actually we have 2 options. The first option, that is the equation looks very complicated, right? But actually, when I use this membership function to demonstrate that, and then you will find that this equation, that is not very difficult to understand. When we look at this bit, remember that this is the height. That means we are going to find out the maximum of this maximum grade of this membership function. So the red line, the envelope, that is the output membership function we have. The maximum, that is, we only have this point. When we look at this point, so the y value, that is 1. Yeah. So mu z, that is 1 at this point. I'm talking about this value. So the first of maxima, when I identify this maximum point, I'm going to scan from the left, that is from smaller z value to larger. So I'm going to scan from this point, and I just find out that the first value of z, which give you the maximum, the maximum height of this membership function, and then I'm going to take this to be the z star. So right here, when I apply this equation, z star, that is 8. Yeah. And now, because we only have one maximum grade right here, and then so this is the first. If we are going to have another membership function right here, another bit, this will give you the same height, and then we have two options. Yeah, we have two options. Either take this one or this one as the z star, but according to the first of maxima, when we scan from the left, this is the first value of z, give you the maximum height. So we take 8 as the diversified output. The last of maxima, we do the same thing, identify the maximum height, and then scan, this time scan from the right, and then so we find out that this is the first value of z, which give you the maximum height of the membership function, and then so which will give you the same result, z star, that is 8. And now assume that if we are going to have a membership function another bit right here, so the envelope, that is something like that. Yeah, so that is the envelope, that is something like, we have 2 points. If we are going to scan from the right, if these 2 points, they are the same value, say 1, and then this point will be the z star if we are going to apply the last of maxima. Yeah. Okay,